The next segment in Chapter 4 will discuss oxidation-reduction reactions as well as concentrations of solutions. So oxidation-reduction reactions. These are reactions that involve the loss and gain of electrons. A couple of examples.
When zinc metal is exposed to oxygen at high temperature, it reacts to form zinc oxide. Electrons are transferred from zinc to oxygen, creating oxide and zinc ions. We say that zinc has been oxidized. The oxidation of zinc by molecular oxygen is an example of an oxidation-reduction reaction. More generally, oxidation corresponds to a loss of electrons. Zinc is oxidized because it loses electrons to the oxygen. On the other hand, oxygen is said to be reduced because it gains electrons.
And then the next example is with zinc.
When a zinc rod is immersed in dilute acid solution, hydrogen gas is evolved and zinc ions form in the solution. The solvated hydrogen ion is represented as the hydronium ion H3O+. In this reaction, zinc is oxidized and hydrogen ion is reduced. When a zinc rod is immersed in an aqueous solution of copper sulfate, a similar oxidation-reduction reaction occurs. In this reaction, zinc is again oxidized. Now, however, copper 2+ ion is reduced to copper metal. In the two examples we have seen, zinc is oxidized. Because it causes the reduction of other substances, zinc is said to be a reducing agent. The substances that are reduced in these reactions, hydrogen ion or copper +2 ion, are oxidizing agents towards zinc.
So if we look at the reactions here and recall potentially from last year, we had the expression Leo the lion goes grr. So losing electrons is oxidation, gaining electrons is reduction. And you can see the two half reactions here for you. So for some practice, depicted below is the reaction between calcium and oxygen. So why don't you write the half reactions for both the oxidation part and the reduction part. Also identify the oxidizing agent as well as the reducing agent. One of the critical parts of doing oxidation-reduction reactions is being able to assign oxidation numbers to the individual atoms. Now, there's some rules for doing this. These are all listed in your book as well. But atoms in their elemental form, the oxidation number is 0. So oxygen in its elemental form, nitrogen, the metal atoms, anything that's not combined with something would have an oxidation number of 0. Any monatomic ion, the oxidation number corresponds to the charge. So fluoride ion, F-, oxidation number 1-. Magnesium ion, Mg2+, oxidation number would be 2+. So those should be fairly obvious. When you have nonmetals, number 3, nonmetals are usually negative. However, they're sometimes positive, so you're going to have to base it on the ion that's present. So there's 3 different listings here under that category. Oxygen, we usually give a -2 except for peroxides, which is an O2-. So oxygen in that case is only a 1-, or -1. Hydrogen is a 1- when bonded to metals, and a +1 when bonded to nonmetals. Halogens Fluorine always has a -1. Others are usually a -1, but in binary compounds, however, they can sometimes be positive. And finally, number 4, remember that the sum of the oxidation states in a neutral compound is always 0. And the sum of the oxidation states in a polyatomic ion always equals the charge of the ion. So here are some examples. So if we look at potassium hydride, potassium is a metal. Hydrogen in this case would be the anion. So potassium would be a +1, hydrogen would be a -1. Sodium chlorate, sodium would have its usual +1 charge. Oxygen gets priority here, so the oxygen would be a 2-. Since there are 3 oxygens, and altogether the chloride ion has to have a -1 charge, the chloride must have a +5 oxidation number. In manganese nitrate, we would assign the oxygen again a 2-, give it priority. The nitrate ion is a -1 ion, so NO3 together has a -1 charge. So the nitrogen here has a 5+. Excuse me, I should have corrected these. When we're talking about oxidation states, we usually put the plus in front, or the charge in front of the number. And manganese here then would be a +2. The most common type of oxidation-reduction reactions that happen in aqueous solutions are single replacement reactions. So here are 2 that occur. The bottom one, the zinc plus hydrogen chloride, we saw in the last video. The reaction between the zinc and a solution of tin 2 chloride is fairly interesting. So we'll take a quick look at that one and see how it works.
Finally, some acidified tin 2 chloride solution is poured onto a piece of granulated zinc. Again, we notice an almost immediate displacement. In this case, we are getting some bubbles of hydrogen produced as well, because there is acid in the tin chloride solution. However, the main thing to notice is that the piece of granulated zinc is becoming coated with fine crystals of tin.
You can start to see the nice shiny slivers of tin in there.
After some time, the tin crystals grow out as needles from the surface of the zinc. These are pointed needles of tin on the surface of zinc.
So it's a fairly interesting reaction. Here we have the activity series, which again is inside your book. And basically the idea here is that as far as the metals go, any metal can replace a metal below it on this chart. In other words, it can force the other one to take its electrons. So in the last example, we had zinc, and we put that into a solution of tin 2. So the tin is more... So the tin is less reactive than the zinc. The zinc is able to force tin to take its 2 electrons. Here's another example of a reaction in which copper is reacting with a solution of silver nitrate to form silver and copper 2 nitrate. So this is another one where you should try and write the net ionic equation. Also identify the oxidizing agent and the reducing agent, and you can, hopefully the half reactions for oxidation reduction are very obvious here. But you should just check just to make sure you can do those.